Okay, now we said range. Mr. Creswell said those are y values. So why don't we take a look at the graph of this one? Can you get us to the... We graphed y equals 2 over x. It took 2 math teachers a good 5 minutes to do that. But if we're looking for the range, those are the y values. So here's my y-axis. Let's say every value here has a spot that corresponds to it on the graph. Even down here, all these spots are also on the graph corresponding to the y-axis, except right along here, the graph never touches it. All right, that's called a horizontal asymptote. It gets really close to it, but it doesn't touch it. So this is not in the range, but all these other numbers are in the range. So I would say, if we're looking at the number line here, all the numbers are in the range except 0. And that's an open hole. So how would you write that, Mr. Creswell?
So I'd probably write, for the range, we're okay from negative infinity to 0, but not including 0. Or we can also be not including 0 to positive infinity. So anywhere in there except 0 is okay.
Very cool. So that's range or y values. Range or y values. Continuity means, is the graph continuous? Can you graph it without picking up your pencil? That's all that means. Is it continuous? Can you graph it? So there are spots where it's not continuous. We say that's discontinuous. And there are 3 different kinds. Removable discontinuities are going to end up with an itty-bitty hole on the graph. All right. Okay, so removable discontinuities. Our example here threw Mr. Creswell and I for a loop. We've got y equals x over x squared plus x. Now let's factor the bottom and say that's x over, factor an x out of both of these terms, x plus 1. Now this thing's going to have 2 problems. It's going to have a discontinuity at 2 different places. And one of them is when this equals 0. So at x equals 0, we have a discontinuity. And another one is when x plus 1 equals 0. Well, what number do you have to put in for x to make this set of parentheses 0? Well, if x was negative 1, we'd have a problem. Negative 1 plus 1 is 0. So x equals negative 1, we have an issue there too. I'm going to make the conjecture that this one is removable because you can cancel those 2 x's out. So you can remove it. So really, your graph at x equals 0 is going to have a little hole in it. Now, most graphing devices won't show you that. So let's take a look at the graph. And at x equals negative 1, look, we do have a definitely spot of discontinuity. I'm drawing the graph and then, oh, got to pick my pen up and keep going. At x equals 0, it looks like the graph keeps going, but there should be a little hole right there. That's called a removable discontinuity. I think I kind of botched that one up, but oh my, what a day, huh? And jump discontinuity. Jump discontinuity would be like you're working at some fast food joint and you get $7 an hour for the first 40 hours in a week. But if you work over 40, all of a sudden your pay goes to $11 an hour. That is called a jump discontinuity, or it comes from a piecewise function because the function is defined in different pieces. And we'll definitely delve into those this year. Do you want to talk about infinite discontinuity? You want me to bring this back?
Yeah, so an infinite discontinuity. We mentioned earlier that there's a discontinuity. I got the pen right. There's a discontinuity right here, and it's an infinite discontinuity because if I'm going along, I'm going to have to go to infinity before I can actually pick my pen up. And then the same thing up here, I can't ever touch, what is that, negative 1? Negative 1 at any point, right? So it goes on infinitely.
I liked how you said, I have to go to infinity. To infinity and beyond. All right. So increasing and decreasing, oh, you've got this first one, I think.
Okay, so let's look at the graph of this thing. Let's try. There, right?
Yeah, let's bring it over in case it doesn't. Is that okay?
Yep. Okay. So increasing, decreasing, it's what we're going to look at. We're going to go from the left, and wherever, as we're going to make x get big, 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 and see what happens to y. So if I follow the graph along x, it looks like y is getting smaller, 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 smaller.
So y is going down.
Y is going down, so it's decreasing from here. We'll write this nicer in a little bit. Decreasing there, and so I think that happens the whole time, right? That's not going to change.
No, it keeps on going forever.
Right, exactly.
Way, yes.
So then we look at the rest of the graph, and as x gets bigger, 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 we're still, y values are getting smaller, 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 smaller. So I think we're decreasing from here too, right?
We are, because it keeps going down, down, down.
Down, down, down. Okay? So how do we want to write that?
So what number is way, way out here, Mr. Creswell?
What's
way out here on the x-axis?
Maybe 1?
Maybe negative infinity.
Okay.
You already went to infinity. And then what number does it get really close to on the x-axis before it jumps?
1?
1?
It looks like, nope, 2.
2. Thank you. And then where does it jumps over 2, correct? And then starts again?
Yep.
And then it goes until?
Positive infinity.
Positive infinity. So that would be the domain on that thing. But that would be when it's decreasing.
Right,
correct?
that's the intervals of decreasing.
When is it increasing? Whoops.
Never.
Yeah, this one's increasing. Never. Okay, alright. Do you still use empty set?
No.
Okay, never. Never. Alright. So let's take a look at just y equals 2x. We should all be able to graph y equals 2x just off the top of our head. It goes like that. And which is my graph going from left to right? Is it going up or down? Well, it's going up, 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 up. So it's increasing the whole time, and it increases forever. So I'm going to say on the x-axis, what number's way out here, Mr. Creswell?
Negative infinity.
Yeah, good for you. And then it never stops, so it increases from there to there. So that's increasing, and where does it decrease?
Never.
Never. Never. Is this you?
Ooh, I think we were going to wing this one.
No. We've got a graph.
Right.
We've got a graph. Oh, okay, but we're going to talk about it?
Yep.
All right, so we're talking about extrema. Is that correct?
Extreme.
Extrema. So what does extrema mean?
I think maximums.
Maximums?
Minimums.
Minimums. Extreme cases.
Extreme cases.
Extreme cases. And I'm going to make the conjecture that this is going to be a relative maximum on this graph, this point, because it's the points right next to it are lower than it.
Right.
Does that make sense?
Yeah.
And this one is going to be a relative minimum because the points below it are bigger than it.
Bigger than it.
So why did I say relative max and relative min?
Well, because I can find a point that's greater than this point right here. So, for instance, this point, the y value is greater than that point. So it's not an absolute max. Absolute would imply that there's no more x values that are.
I would say this one doesn't have an absolute max, would you? Because it just keeps going up,
Yep.
up
You can't
forever.
ever find it.
All right, and same thing. I don't think it has an absolute min because it keeps going down, 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 down. So I would say this probably has an absolute max. You suppose that's 0.5, or a relative max. Relative max at x equals 0.5, and a relative min at x equals about 1.5. Yeah, we're kind of taking a guess there. If we get our graphing calculator situation.